In this section we're going to discuss some of the introductory aspects for projection to volumetric data in CT. Now, we've previously discussed the evolution of the Beer-Lambert law. So we start with the simplest form where we have monoenergetic X-rays and a homogeneous material. As we go to an inhomogeneous material, we see we then have to integrate as a function of ray path from the source to the detector, that's S to D in the equation, to incorporate the change in attenuation coefficient. And as we go to a polyenergetic source in an inhomogeneous material, we add this second integration, which is an integration over the energy distribution of the incident X-ray source. So we know the aim of the exercise in the reconstruction process is to get a map of mu, which is the linear attenuation coefficient. We then apply the Beer-Lambert law to that and convert it to a property with Hounsfield units that's scaled relative to water. So we've seen our simplistic version of our acquisition and reconstruction steps, and we saw previously that we then have to introduce a couple of more steps in here where we deal with the fact that we have helical data and also a divergent fan beam geometry in our third generation scanners. Now, mathematically, we're talking in terms of the radon transform. So we know that our reconstruction is going to be on a Cartesian grid, and that Cartesian grid is related to the cylindrical geometry of the scanner, and we talk in terms of these ray paths, which are line integrals. So the experience of the X-rays integrated along a line results in the number, the detected intensity in the detector channel. Now we know that in order to solve in terms of the radon transform, we introduce the Fourier transform, and we have this relationship between the 2D Fourier transform and the 1D Fourier transforms and our Fourier slice theorem, which was the first iteration of solving the reconstruction process. So the Fourier slice theorem isn't widely used anymore. We moved to filtered back projection and then on to iterative reconstruction, which we're going to discuss in more detail here. But we're just going to flesh out some of the mathematics that we've seen previously in terms of the Fourier slice theorem, so that when you encounter these in textbooks, you know what the nomenclature is and the basic concepts behind these ideas. Now we know the Fourier transform is used in order to describe two things: either the construction of a waveform in terms of waves of fundamental frequencies, or taking a composite waveform and deconstructing it back into its fundamental frequencies. So we either talk in terms of the Fourier transform or the inverse Fourier transform, depending on which way we're going. And we know that in our previous discussions we talked about both the temporal form of the Fourier transform. So we discussed plucking guitar strings to give you a nice intuitive way of understanding Fourier components, and then we also talked about it in terms of the spatial domain, which is what we're discussing in CT. So clearly we're not talking about things in terms of plucking guitar strings anymore, but in terms of the spatial frequencies in an image. And we saw that there's a basic recipe in the Fourier transform. So if we want to know the energies of the frequencies in our signal, we can take our signal, our input signal, f of x, multiply by a complex exponential, and integrate. We also saw that this was discussed in terms of the Euler representation. So the Euler representation is one of the most useful formula in mathematics and simple physics as discussed here, and it allows us to take something that's discussed in terms of sines and cosines, so things that oscillate, and describe them as a complex exponential, an e to the I something. And we do that because it gives us a nice compact representation that's easy to differentiate or integrate. So the basic form, as we can see here, is e to the I phi is cos phi plus I sine phi. So we have the cosine components as the real components of the signal and the sine components as the imaginary components, and we can bundle those two things up together. Now, we're going to go back over the Fourier slice theorem just to familiarise you with the mathematics of it. So last time we didn't discuss any of the mathematics, we just showed a couple of pictures. So now when you're reading through the textbooks, you're reading through the more advanced sections of the textbooks, so you need to understand what the equations are trying to tell you. So here we can see I've colour-coded the projection data as the green part of the equation there and the original object as the red part of the equation. And we're just going to look at a derivation that then relates the one-dimensional Fourier transform properties to the two-dimensional Fourier transform of an object and its inverse. So let's consider the diagram in the top right hand part of the slide, but imagine it's reset back to theta equals 0. So we're just considering the start point of our scanner where all of our line integrals are then parallel to the y-axis. Now we have an object in the scanner, f of x, y, and clearly we don't know what that object is. We're going to scan this object, and this is the thing that we want to get back to after our reconstruction step. So what we do have is our projection data. And we have our projection data, as I said, we're just considering the projection data at the moment with all the lines parallel to the y-axis. Now we can take the Fourier transform of this, and by applying our recipe, so we multiply by a complex exponential and then integrate. And then that then gives us our one-dimensional Fourier transform, which we can see as two representations here. In the flow diagram at the bottom, we can see it in the representation where we have the frequencies shown as a spike, so we have the amplitude of those frequencies, or the power of those frequencies, on the y-axis and the frequencies on the x-axis. Or we can see them in a colour-coded bar on the right-hand side of the image there. Now we know that that colour-coded bar represents the line parallel to the x-axis on the right-hand side of this slide here. So before we get back to that, let's remember what we've previously discussed. We've discussed we can have an image, such as is shown on the left-hand side here. That image can be Fourier transformed, and we end up with the Fourier transform on the right-hand side here. So on the right-hand side we have frequency on both axes, and we have low frequencies in the middle and high frequencies going radially outwards in all directions. Now, if we just consider the strip indicated by the red dashed line here, which is parallel to the x-axis, then we effectively have just the middle strip of the two-dimensional Fourier transform. So there's no y component to that strip of the Fourier transform. Now, if we take that middle strip and compare it to what we've showed previously, which was the first step of the Fourier slice theorem for our scanner at theta equals 0, and we compare those two, what we see is that we get the same answer. So what this is telling us is that the configuration of the scanner, where all our ray paths are parallel to the y-axis, shining through the object, we collect that projection data, take the Fourier transform of that strip of the Fourier transform that we end up with is the same as the middle strip of the two-dimensional Fourier transform. And if we do that at all angles, we see that the angular distribution is conserved. So that then means that we can effectively build up the two-dimensional Fourier transform of our resulting image just by repeating those steps at each angle. And once we have the two-dimensional Fourier transform, we know if we want to get back to the original image, all we have to do is invert that Fourier transform. So here we can see we've proved mathematically that we can, by applying the Fourier slice theorem and collecting our projection data at each angle, taking the Fourier transform of each of those and laying them in a grid, we can end up with a two-dimensional Fourier transform, which we can then just invert to get back to our real image. And that's the proof of why the Fourier slice theorem works. And here's what the recipe looks like. So this is the basic recipe that we encountered last time, except we didn't give any of the formal proof of it last time. So now we've proven it. Now, there are a couple of issues with the Fourier slice theorem. The first is that it's difficult to implement as an efficient algorithm, and the second is it's prone to errors because we have to interpolate in the Fourier domain in order to regain that high frequency data that's missing in the bicycle spoke representation. And a much more numerically stable form of the algorithm that's become the workhorse in CT reconstruction was derived, and that's the filtered back projection. So filtered back projection is an analytic solution to the reconstruction problem, and that says that what we want to do is undo the projection. So we've collected projection data. Can we just undo it by pushing the projection data back into the grid, by smearing it back and effectively undoing what the X-rays did? And as we know, we can do it provided we know an analytic form of the point spread function, which allows us to undo the blurring that's associated with that geometry of the CT scanner. So this is what it looked like pictorially. Here we had a phantom which had a circle, a square, a dot and a line in it, so we imagine that's the inside of the patient. We've collected some projection data at 45 degrees, just as an arbitrary example, and that's what the projection data looks like. And we can see that the section that's circled with the red dashes would be the rays passing through the square in the object. Now when we take that data and we push it back into an empty grid, we've pushed the data back into the square, but we've also pushed it back into all those other pixels that are highlighted in red there, which didn't contribute to the data from the square in the first place, and that's what gave us the blurring that we had to undo. So we saw that effectively what we end up with is too much low frequency data, which means blurring and smearing in the image, relative to the high frequencies in the data. And we talked about applying a ramp filter. So the ramp filter has two representations. On the left hand side here we can see the frequency representation. On the right hand side we can see the real space representation. So the real space representation looks a bit like a Mexican hat. On the x-axis we just have detect a pixel location effectively, which is just a coordinate in real space, and on the y-axis we have the amplitude of the filter, and on the left hand side the ramp filter in its frequency domain looks like a ramp, which is why it has the name ramp filter. So it's small at low frequencies and increases linearly to high frequencies. Now we also saw that if we apply a filter like this with a hard cutoff, one of the issues that we have is that we get artifacts in our reconstruction. So whenever you're doing Fourier transforms, we don't like harsh cutoffs in the frequency domain. We have to smooth that edge out, and we did that by combining the ramp filter with a Butterworth filter of some kind or a Han filter, and smoothed that over at high frequencies so it curves off gently back down towards zero, and it stops the ringing artifacts appearing in the resultant image. So we've seen we can apply the filter in two ways. We can either apply it as a convolution, which is shown on the bottom there, and you can do that, can be done just simply in an Excel spreadsheet. You take your kernel and your projection data and you slide the kernel across the projection data and you cross multiply and you sum as you go across. Or alternatively, you can do it in Fourier space as a multiplication using the frequency representation. And here's what the two look like. So the top form of the equation here is the convolution in real space, and the bottom form of the equation is just a multiplication in frequency space. So we take the Fourier transform of f, the Fourier transform of g, multiply the two things together in frequency space, and then obviously take the inverse Fourier transform to get back. So this is what our filtered back projection equation looks like. So if you're reading a textbook and you see an equation that looks like this, it is the filtered back projection represented mathematically. So you can see we've taken a Fourier transform of the projection data, which is our capital P here. In the text that we've taken this from, a lowercase p was the real space representation of the projection data, and an uppercase p with frequency in the brackets, which is omega, there is clearly a Fourier representation. We can then multiply that by a filter, so that's our omega, so that might have been the ramp filter, or that might be some other filter, of the combination of the ramp filter with the Butterworth, etc. And then we inverse Fourier transform. So again, we're multiplying by a complex exponential, as we saw in our recipe, and we integrate. So whether that be the Fourier transform or the inverse Fourier transform, it's just a slightly different form of the complex exponential, and we're integrating this time with frequency instead, as we're inverse Fourier transforming. And then clearly we have to do this at each projection angle, so we sum over all our projection angles, or we integrate over the projection angles. So this is what our filtered back projection algorithm looks like as a flow diagram. And now clearly we need to move beyond that. But what we've covered so far is a recap of what we've previously discussed, but with an introduction to what the mathematics looks like. Now we're going to move on to part 2, which is going to discuss iterative reconstruction, as opposed to analytic forms of the reconstruction that we've previously discussed. So to summarize what we've seen in part 1, we had some projection data, we've looked at the Beer-Lambert law and its multiple versions. We've looked at a more detailed version of the Fourier slice theorem and a more detailed version of filtered back projection. And we've alluded to the fact that we're now going to move on to what's now become the current state of the art and the current workhorse, which is iterative techniques in reconstruction.